on time by starting on time. So this is more of a science talk than I think many of the talks you've gotten so far, but I'll try to talk a bit more than I would typically about the ideas underlying VLBI and how we do VLBI than I would normally. I think I'm going to try to plug in my clickers. Let's see if this will work. Okay, so you've probably all seen this image by this point, but this is the Event Horizon Telescope image of M87, the first image made of a black hole. So this is a very long baseline interferometry image, and obviously in some ways the most amazing aspect of this is the diameter of this ring, right? So that's 42 micro arc seconds. So that's incredibly small. It's about 1/10 billionth of a circle. And obviously much higher angular resolution than you can obtain with an instrument like the SMA by itself. And so that's why VLBI is important. The same principles that allow us to get higher angular resolution by moving antennas to larger distances up on the summit of Mauna Kea use the same underlying principles of interferometry, and we put antennas around the world, and we build a telescope as large as the Earth in order to get that angular resolution. So we actually achieve a resolution of about 20 micro arc seconds. It's about the width that you see in this ring, and the black hole is contained within this ring. So there's a central depression here, which is where the black hole is located, and the diameter of the ring actually tells you exactly what the mass of the black hole is. This is a straightforward prediction from general relativity. You measure this diameter, and you get a mass for the black hole. Well, you need to know a distance as well, and you can put those together. 6.5 billion solar masses. In addition to being the first image of a black hole, it's one of the best, if not the best, confirmation of the existence of black holes, because all of that mass of the black hole has to be located within here. If you think, well, I'll show you in a minute some of the other evidence for black holes. This obviously got a lot of attention when we announced it last year among the many different places around the world that contributed to this. So this is from Taiwan, obviously from the United States, from Chile. And in fact, there was, global response, and it's the astronomical image that launched 1 million memes. And I in particular like this one from XKCD because, like many good XKCD comics, it actually includes a little bit of science information that you wouldn't have ordinarily thought of, right? And so to scale, the ring is slightly larger than the solar system. That's a pretty interesting way to think about it. Also, the Eye of Sauron. Some people saw that. Some people saw cats in it. Anyway, if you were like me, by April 11th, this is how you felt. Really kind of an overload. But it's been a very exciting year for the members of our collaboration who participated in this. And there are many of us. This is about 40% of our whole collaboration. We had our collaboration meeting, our annual collaboration meeting here in Hilo back in December. Some of you may recognize this view from the Naniloa Hotel This part may be underwater right now, but in December it was above ground. And of course, you know, in order to do VLBI, one of the things that I love about doing VLBI and that got me started in doing this 25 years ago is that it's a very hands-on kind of activity that you have to go to the telescope and make it work in order to do this. It really is experimental. We talk about doing experiments, and that's in part because we're not sure if it's going to work. But it also means we get to go to telescopes. And so you can see some of us at the SMA. There's another time from at the SMA, the Pico Veleta telescope in Spain. This is ALMA, the LMT, the South Pole, and this is SMT in Arizona. And I want to emphasize that Hawaii and Mauna Kea have played a really big role in this. This is about half of the people here in Hawaii who contributed directly to the project, and so you may see some of these people sitting here in the audience who have made contributions to this. It really is. We are a 300-member collaboration. There were 347 people on our paper, and really wide range of contributions to doing this work. And so both SMA and JCMT and the people at those institutions played really big roles in this. So scientifically, the story, I think, really starts with the Galactic Center, right? So this is a long wavelength radio image of the Galactic Center. This one was made with Meerkat, South African centimeter wavelength interferometer, actually a truly spectacular new telescope. So the galactic plane goes like this. Sagittarius A star, the black hole at the center of our galaxy, sits inside of this saturated region. It's not actually saturated because of Sagittarius A star. There's a supernova remnant there, which is producing most of the emission that you're seeing. And buried inside there is the 4 million solar mass black hole. And how do we know that there's a black hole there? Well, the most compelling evidence has come from stellar orbits. So this is the orbit of a star known as S2 that in 2018 took its second close passage of Sagittarius A star that's been measured. It's in a 15-year orbit. It goes around. You can measure its orbital properties, and you can measure the mass of the black hole. We know the mass of the black hole and the distance to the black hole to better than 1%, which is truly spectacular. And fortunately for us, Sag A star is bright, has a radio millimeter wavelength source, so it's detectable. And then there's one other source, and it's also very large on the sky, so it is a source that we can resolve using the EHT, which I'll explain to you how that works in a bit. The other source is M87, the source that I showed you the image for already. And M87 is in the Virgo cluster. It's at a distance of about 17 megaparsecs. And it has a mass, well, there were two different methods of estimating its mass prior to our measurement, between 3 and 7 billion solar masses. And the shadow diameter is just directly related to the ratio of the mass over the distance, and it comes out at the scale of 20 to 40 microarc seconds, depending on which mass estimate that you use. Now, M87, of course, is a very different kind of galaxy than the Milky Way. It's a central galaxy in the Virgo cluster. It's an elliptical galaxy, very massive galaxy. And you can see this very strange feature that was seen a century ago in the optical, and that's a relativistic jet that's coming out of the center of the black hole. That is a very clear feature in the radio. So this is a a very long baseline array image at a wavelength of 43 gigahertz that shows you incredible detail and structure in this jet. The black hole is down here, and it's powering this relativistic outflow that goes out and is actually seen on a megaparsec scale, on the scale of the entire galaxy cluster. It has its influence. And so our image comes from this very central region down here. Fundamentally, what we're looking for when we make these EHT images is we're looking for the effects of general relativity in terms of the mass of the black hole bending the light that's created near the black hole. And so these lines are showing you the orbits of photons that originate close to the black hole. And so you can see photons orbit black holes. It's a pretty incredible idea, right? That it's, you point your laser, the light goes straight. You point your laser next to a black hole and the light gets bent. And that's what produces this shadow feature. And so it was predicted in the 70s. This is actually a hand drawing made by a researcher prior to the advent of computer visualization of these kinds of things, but of his calculations. And so that's why that's so important. And then, of course, as our technologies advanced, we continue to produce simulations that reproduce these basic features of the image. Okay, so the role of Mauna Kea and the JCMT and the SMA is quite important in making these measurements. So there were two watershed measurements, one of Sagittarius A star and one of M87, using Karma, rest in peace, and the SMT and the JCMT. So three element interferometer. The SMA's role in this and in the other measurement was the SMA provided the clock. JCMT did not have a maser. SMA provided the clock, and JCMT provided the aperture. And you can see, right, so this is visibility amplitude versus baseline length, and you can see the very limited amount of information that was collected, but that gave us a characteristic size. We fit a Gaussian to it and got a size. We didn't make an image. We did the same sort of thing with M87, similar kind of data, similar observing array. And again, we measured a size a few times the Schwarzschild radius from both of these. So since we did those measurements, the push was really to get from making measurements or constraints in the visibility domain to actually making images. And so what's required for that? Well, the first thing is to think about this shadow size. It's somewhere in the regime of 50 microarc seconds, as I've said. And so how do you get that angular resolution? Well, you need, at a wavelength of about 1 millimeter, you need a 10,000 kilometer baseline in order to get an angular resolution around 20 microarc seconds. That's kind of the bare minimum of what you need. And if we lived on a slightly smaller planet, we wouldn't be able to do this. So we're quite fortunate to be able to reach even these two sources because of that. Now, I mentioned the very long baseline array. There's a VLBI antenna on Mauna Kea, but the VLBI only works up to a wavelength of 3 millimeters. That's the shortest wavelength at which it works. And so that provides, even on global baselines, that provides insufficient angular resolution to make this measurement. So we had to create our own ad hoc network out of existing sub-millimeter, millimeter wavelength facilities around the world. I think it's already been emphasized to you that, of course, that doing things at millimeter wavelengths is hard because of the atmosphere. The atmosphere is opaque, except for at special places on the planet, high altitude locations, high and dry locations. And the atmosphere is turbulent. And so there are phase distortions on very short time scales. And in VLBI, that problem is much, much worse than it is for a connected element interferometer, because we have a telescope in Hawaii, we have a telescope in the South Pole, and the atmosphere is totally uncorrelated between those two places, right? You have two telescopes that are 100 meters apart. As a cloud moves overhead, there's going to be some correlation in that cloud structure over your two antennas, but at a distance of 10,000 kilometers, there's no correlation. And so the time scale for variability, you can't read this axis, but it's a few hundred seconds here. You can see the phase varying. The time scale of variability is about 10 seconds on which we need to be able to detect the source and correct for atmospheric phases. So that makes this very challenging and limits the sensitivity. The other problem is that millimeter wavelength antennas just aren't very sensitive. They're small, and the atmosphere is bad, and the receivers are noisy, and our sources, even at 1 Jansky, are difficult to detect in this kind of 10-second time scale. And so, to make progress, we really required new telescopes, new, more sensitive telescopes, and increases in the bandwidth. And so, of course, ALMA was really transformative for what we did. The introduction of ALMA has really changed the game for doing this, because the baselines to ALMA are so sensitive, and within 10 seconds we make very rapid detections. Now, both ALMA and the SMA we used together in what we call a phased array mode. And what that means is that we didn't attempt to connect one SMA antenna to each element of the array, but what we did was we summed together the signal from all the SMA antennas and made one signal out of that and treated that as a single station. Now, in order to do that, that meant we had to apply our phase calibration on the fly as we go, right? That because if you're not correcting for those local atmospheric differences between two antennas that are 100 meters apart, when you add those signals together, they'll be out of phase, and they won't constructively interfere. And so this is an example of what that looks like when it works. That as you add in, as you sum together more and more telescopes, you see the signal to noise ratio going up as predicted here by the theory. And so this was for the SMA and for ALMA. This requires custom hardware and custom software to carry out this this phasing step. And so this is done within the swarm correlator hardware, and using at the SMA and separate system at ALMA. You can see what we call the phasing efficiency, which is sort of if you add everything together perfectly, how much signal would you get dividing into what you actually get when you add things together. And if we don't have the phasing system turned on, then you see you get very poor efficiency, a few %, just because all those antennas are uncalibrated. But then you get up to about 100% efficiency. It does better in better weather, and it does better if you're looking at a very bright source, where in a short time interval you can measure the phase very accurately, quickly. The other really important aspect of this kind of experiment is that the antennas are not connected together, right? The SMA operates by fiber optic cables that are run underground from the antennas back to the back to the correlator, and the signals arrive instantaneously, or but we can't do that between Antarctica and Hawaii and Chile. So what we do is we write our data onto hard disks, and we write data at a rate of now at a rate of about 64 gigabits per second. That's about 4,000 times faster than my home internet connection. You know, we, in the course of a 5-day experiment, across our 6 to 8 stations that are participating, we write petabytes of data onto these disk drives. So we have these custom systems. Each one of these cartridges here has 8 hard drives in it. Each of those is an 8 terabyte hard drive, and we're streaming to each one of them simultaneously in order to write at this very fast speed. When I got involved in VLBI here in the mid-90s, we were still using magnetic tapes, these giant reel-to-reel tapes, and you had to, every 2 hours, you had to get up and change the tapes, and it was really a harrowing experience. You had a few minutes in between scans to do this, and you're very tired. In the early days, the very early days, people used essentially video cassettes. They used commercial video cassettes, and they were operating at about a megabit per second. All of this is, and especially this extension in the total bandwidth, is Moore's law. It's really driven by commercial industrial investments in computing and data storage that has enabled this continual growth rate. The other aspect of the arrays not being, or the elements of the array not being connected, is that we don't have a common clock, right? That the array works by, interferometry works by having the same frequency standard at each antenna, right? If you have an error in frequency, then that leads to a decorrelation in your signal. But we can't share the clock amongst all those antennas in any simple way. So what we do is we have the best frequency standard that we can generate independently at each one of these sites. And it actually is a hybrid of 3 different types of clocks. On the longest time scale, we use GPS. GPS is incredibly stable on very long time scales. And in fact, what we do is we use it to generate a 1 pulse per second, which everything is synced to. And then on time scales between about 1 second and 1,000 seconds, we use hydrogen masers. Hydrogen maser is a very sophisticated apparatus that has the goal of putting very low temperature, very undisturbed hydrogen atoms into this quartz bulb and wait for them to radiate at 1420.40 megahertz and generate that spin flip transition, which you can then translate into your fundamental reference signal. Hydrogen maser is really central to this. And then on the shortest time scales, crystal oscillators are the frequency standard that you connect to. So it's a hybrid between these technologies that allows us to get very, very stable time and frequency. Okay, so here's the experiment we did in 2017 that imaged M87. I've already mentioned all these facilities, I think, so I don't need to say anything more about that. And then this is what the data looked like. And you know, for someone like me, who did a lot of 3 baseline, 2 baseline, 1 baseline interferometric experiments early on, we knew exactly what we had when we saw this visibility amplitude versus baseline plot. So there are a few really key features here. One is that there are 2 nulls that you can see, one at about 3.5 gigalambda and one are just short of 8 gigalambda there. those look like the ringing nulls that you get from a Bessel function. And what is a Bessel function? A Bessel function is, or one Bessel function is a Fourier transform of an infinitely thin ring. You also get nulls like this if you have a disk, a filled in disk, but they're at a different separation than what you see here. And so we could immediately say that this wasn't a disk of emission, but that it looked more like a ring of emission. The other thing that you can see is not everything is perfectly following these dashed lines, which are what you expect from a thin disk of emission. So in particular, this emission right here, and that tells us that the emission was, that the ring is not perfectly symmetric, right? That it's brighter on one side than it is on the other side. And the location of those two nulls also, we can use that to tell us what the diameter of the ring is. And so you can put all that together, and a lot of the basic details of what we saw, you can read off of this diagram. It's ring-like, there's some asymmetry. We're missing large-scale structure, right? This is SMA baselines, where we get about a Jansky, and then the next extended baseline, we're down to below half a Jansky. Some part of the jet is missing from this and could be detectable in the future. And then we can read off the size from this. This is a cool demo that we did of kind of showing the relative contributions of the different elements. And you can see that you know, as the Earth rotates, we're filling in the UV plane, we're filling in this visibility amplitude space, and you can build up a better and better image. Now, that's not really how the image gets made, but it does give a sense of the relative contributions, that if you only have a single baseline, you've got really incomplete information. But as the Earth rotates, you get more and more complete information that allows you to build up this image. And really, we just marginally had enough information to be confident that we had this measurement. You've gotten some lectures on imaging. I think one of the really cool things that we did as part of this experiment was we used all the different tools. We used clean-based tools, and we used what we call regularized maximum likelihood methods, things like that look like things like maximum entropy and other techniques. All of them gave the same image, and then we got the same image on multiple days. Okay, in order not to eat into the next speaker's time, I have reached the end. So the future of what we're doing is of course quite broad. That we have Sagittarius A star. We'll be getting you that image soon. We're going to be doing polarimetry on sources. We've looked at a lot of AGN. We've looked at the Galactic Center pulsar. We have multiple epochs of data to come. We want to make images or higher fidelity images. We want to make movies. We want to go into space and do things like that. But with that, I will bring this to an end. Any questions? Rod.
So you had that little image of all the baselines looking at the same time. So how much time did you actually get on source with every single antenna? Station.
Oh, with all the stations all at once?
Yeah, all at once.
Oh, pretty limited. Maybe about an hour of the about 8 hours of which we lacked and which we observed, right? Because you can see, you know, we went from Pico Veleta here in Spain to Hawaii. That's our longest east-west baseline, and we're almost antipodal, or not antipodal, but almost you know, 12 hours apart. So very little time in which we're able to get both of them. But really critical, actually, to get just that little bit. Yeah.
Was the shortest baseline point used in the imaging?
No, it wasn't. You know, one of the things we want to do in the future, and which we will actually do this year, is we have more. We're adding in stations. So Kidd Peak in Arizona, NOEMA in France, the Greenland Telescope in Greenland, and in particular, Kidd Peak to SMT is a few hundred kilometers, and the European baseline, Spain to France, is about 1,000 kilometers. We're hoping that that's going to fill in some of those shorter spacings, and we might start to see the connection between the ring and the jet. Yes?
Would you have a plan to observe the higher frequency to improve the resolution, or is it hard due to the weather?
It is hard due to the weather, but it is our plan to go to higher frequencies. And so actually next week, we're going to be carrying out a test at 345 gigahertz. And so that will be a 50% improvement in our angular resolution. It's tough. There are fewer sites that have 345 gigahertz available. And of course, the weather is worse almost everywhere at 345 as opposed to 230. You know, but that's what we'd like to do. And then there are a handful of sites where we might be able to do even higher frequencies from the ground. So the South Pole, Alma, Mauna Kea, the summit of Greenland, if we move a telescope to the summit of Greenland. Those are sites where we might be able to do 420 or 690 gigahertz and get even higher resolution from the ground. That will be very, very tough. And then longer term, people are talking about putting terahertz satellites in space to do VLBI in space. Yes.
How big of a dish in space would you want?
Because you can get it. You know, the great thing about VLBI is that the sensitivity on a baseline is the geometric mean of the sensitivity of your two stations. So we can put a relatively small antenna in space, and as long as we can phase it, we can connect it to ALMA or phased SMA or phased NOEMA, we still, you know, we get a reasonably sized antenna. So, you know, practically, you know, a few meters for a terahertz antenna is as big as you're going to get anytime soon, right? And so that's the kind of scale that people are thinking about. It's pretty long term to do that. There are a lot of technical challenges to make that work. Yes.
One last really quick opinion question. Do you have any thoughts about the Atlas telescope which has been proposed relatively recently? It's like basically a 50-meter class version of JCMT at the Atacama site.
Oh.
Would that be helpful for EHT type observations? Or?
More collecting area is always good. We are, you know, our ability to make high quality images from the ground is mainly limited by our UV coverage. So a telescope at the same site as Atacama, if it's within, you know, a few tens of kilometers of ALMA, is not going to add a lot. It's not that it won't be useful. We would certainly put it to use. We use OPEX, which is essentially co-spatial with ALMA. You know, I think, you know, getting out to hundreds of kilometers is kind of the interesting scale for us. Any more questions? This is way more interesting than my next talk. So. Yes.
Did you need the success of this before you added on those additional telescopes you're thinking about adding on? Why?
Well, that's an astropolitics question, and yeah, I think there's no way we would get the support to include additional telescopes, or it's much harder that without having, you know, something that you can point to and say this actually works, and it produces science that's exciting, so yeah, you know, I will say, you know, when we were backwards here. You know, how excited were you when you saw this figure? Right? And that's where we were, you know, a decade ago, right? We worked really hard, really proud of it, but that did not end up on the cover of the New York Times. You know, so, you know, it's definitely the case that images have impact, and, you know, and there is a lot more information in that image than what's present here. Okay, I guess in the interest of time, I should move on to this next talk.